Hi folks, Radhakrishna here. Today we're going to calculate the data volumes, how much data it takes for map makers to disseminate all the huge high resolution data that you browse on Google Maps every day, or Bhuvan or OpenStreetMaps for that matter. Okay, so now to quantitatively calculate the amount of data, we need certain grid convention. Okay, so I am going to take latitude longitude convention, standard convention. So this is the grid I've drawn here, and I'm imagining the whole earth is actually mapped in this grid. So this is latitude convention is minus 90 to 90 and longitude is minus 180 to 180. Equator and Greenwich are in the centers. Okay, so now what I am trying to do is I am trying to calculate the distance at the equator spanning this grid from left to right. So what will be that distance is actually, if you imagine Earth, right? So that is basically the circumference of the Earth at the equator. Okay, so that's what I'm trying to calculate here, and then we'll arrive at how it's helpful. So the radius I'm assuming is 6,400 kilometers, and all this calculation is approximate. So at equator, circumference will be 6,400 into 2 into pi, which is 2 pi r, and which is 40,182 kilometers. Okay, so this is the distance at the center of this grid. Right now, I want to divide this whole grid into atomic units so that I can calculate the data for that atomic unit, and then I can scale it across this grid. Right. So for x extent, what is the range? We have 180 minus 180, which is almost 360, right? So I want to divide this grid into 360 parts in the x direction, and it's the same for y direction, which is around 180 parts, right? So in the x direction, we have 360 parts and circumference is around 40,192 kilometers. So in 1 degree will represent at equator almost 111 kilometers, right? So 1 degree is representing 111 kilometers, and now I want to assume that x and y direction distances are equal. This is not the case, and this value is also applicable only at the equator. Okay, but for calculation we can assume that, and so for let us assume 1 degree grid is actually representing 111 by 111 kilometers. Now we have this atomic unit, the grid, right? Now what we want to do is calculate the amount of pixels and data that a satellite image has to have to fill all this grid uniformly. Okay, now we want to calculate this thing. This is the satellite image, which is basically 2D matrix, and for each pixel how much data it covers on the ground, that is called spatial resolution of a satellite image. Let us assume it is r meters. Okay, so I am assuming a satellite image, 1 pixel is covering r meters on ground, right? So how do you calculate number of pixels in 1 degree grid? Okay, so we have 111 kilometers in the x direction, but satellite image is calculating r meters per pixel, so it is 111 kilometers by r amount of pixels in the x direction, and it's the same for y direction. So number of pixels will be x into y, right? So number of pixels is x into y, which is 111 by r into 111 by r kilometer by meter. So we have this calculation. Okay, but now on average in Google Maps, you see in land mass or land area, we see around 0.25 to 0.3 meter resolution. So let us take it as 0.25 meters and then calculate how much amount of data we've got, right? So if r is 1 by 4, substituting in this equation, we get 444 into 10 cube whole square, which is around 2 into 10 power 11 pixels. So this is the amount of pixels in this 1 degree by 1 degree grid. Okay, now we want to calculate what is the amount of data per pixel, right? Because we've got number of pixels here. So what is the data amount of per pixel? So in any standard image, we see colors. Color is made of 3 bands, so 3 values, right? So each value, how much range we can get. So usually it is 0 to 255, which is 8-bit image or 1 byte image. But for satellite data, there is usually more precision and accuracy. So we can, on an average, it is 2 bytes, right? So for 1 pixel, it is 2 bytes, and I'm assuming it is 3 bands. For some of the satellites, there are even 256 bands also. But for here, color images, just RGB, we got 3 bands. So total is 6 bytes of data for a pixel, right? So we've got this many amount of pixels. So data in 1 degree grid is number of pixels into number of bytes, which is 12 into 10 power 11 bytes. And we know 10 power 9 is 1 GB, 10 power 12 is 1 TB. So around 1.2 TB of data. So 1.2 terabytes of data makes 1 degree by 1 degree grid of 0.25 meter resolution. Now what I want to do is scale it across this grid, right? So this is the grid I have got, and how many number of grids will be in here, right? So for example, let us take for one latitude array, there are 360 grids, right? So for one latitude it is around 360 to 1.2 TB, which is 432 TB. But there are how many latitude arrays like that? 90 minus 90, which is almost 180, right? So 180 in y direction, 360 in x direction. So 180 into 360 into 1.2 TB, so it's almost 78 petabytes of data. So we have 78 petabytes of data that can cover 0.25 meter resolution of global maps, right? So that is the amount of data that we're talking about. So almost all map providers who are serving that resolution data have this amount of data in data centers. Now for 1 meter, we can just calculate for r is equal to 1, it is going to be 19.5 petabytes of data, and for any resolution it is around 19.5 by r square petabytes of data. This is a very interesting thing, right? This is a huge amount of data in data centers of storage, but on phone it is very quick. It is around milliseconds, right? You can just scroll it and you are able to see all the maps. How does that happen? That is the question for this video. There are multiple strategies that we can follow to do such streaming of data, and this question is actually for you guys. So think about it. How is this data streamed to all different users who are querying different areas, right? And how does that happen at that huge scale? Almost lakhs of users are there. How does that happen? So think of some strategies and put it down in the comments below, and I will solve it and I will give some strategies in the next video. So let us see how many of you get some of the good strategies for solving this problem. I'll meet you in my next video. Bye till then.